So there we go. So let's talk about what's going on with this particular lab. And this is a topic, there it is, freezing point depression. Okay, you see the title there, but it's actually one of many different properties that are collectively known as colligative properties. And these are properties that they change as you go from the pure substance to the solution. Okay, like for example, what we'll be using over and over again to do this to measure the depression of the freezing point of these different solutions is we're actually going to use a property of a saltwater solution sitting right here. You don't need to know this, but I was sort of messing around trying to gather some information, and I thought this might be useful / interesting / relevant. I don't know. But, this is a type of phase diagram that you see here. It's not a traditional phase diagram. Traditional phase diagram has pressure over here and temperature down there, and it goes solid, liquid, and gas, and there's these different areas on a phase diagram. Okay. What we're seeing here is it's not for a pure substance, it's actually for a solution. It's a brine solution. That's what we're going to use to try to freeze these other solutions that we're trying to study. And what you can see is that there's a temperature plotted versus the concentration of the sodium chloride. And notice that this at 1 or 0 degrees Celsius, that would be pure H2O. We know pure H2O freezes at 0. And notice what happens as I start adding, right, as I'm going across the x-axis, that means I'm increasing the concentration of the salt. And at some point, I reach this thing called a eutectic point. And that's just simply the lowest freezing point for this particular solution. And it comes in at about 23.3% by weight. Okay. And I kind of did that for this solution. And hopefully I'm kind of just pushing technology just to see how well it works here. So far, so good. But we have all right, this is that program that we used last week in the 312. Today we're using it on the iPads, and I think it's going to work more. It's going to work better. But I've had my temperature probe in my ice water, and I tried to get to that 23.3% or so. Okay, and you're not seeing it right now, but it says it freezes about 21 degrees Celsius. And yet you can see that if I start this and look at the temperature, it's coming in at about -6. Okay, so it's just appreciation that when you get this that thing I'm causing the freezing diagram, that's under really controlled conditions, pure water, pure salt. You're freezing it from the outside, and you're monitoring the change from this liquid to solid phase. But it kind of gives us an idea that, if we can get to that point, we can get a fairly low temperature. And this is just ice water with salt. And I can't really fully explain this phenomenon, but for whatever reason, as you start mixing this with the thermometer, it actually decreases in temperature. All right. And the coldest I could get this was about -14 degrees Celsius, which is pretty cold. I mean, probably freeze a beer is my guess. Anyway, and that's basically what we're doing for this reaction today. Right? We're going to make up these ice baths. We're going to make up different solutions, and we're going to put that in the ice bath, and we're going to try to freeze the solution that we make up. All right? And we're trying to study this thing called colligative properties. Let's get back to the lab so we can look at some of the details of it, some of the calculations. And you can see there's a lot of different colligative properties. We're only looking at freezing point depression today. In class, we'll also, I think we do a calculation with boiling point elevation in class, I believe. So freezing point, depression here, boiling point, elevation in class. Both of them would be on the test for next week. Okay, so these freezing curves that you will see today look something like this. There's just oodles of different ways to plot data in the world. And this one, you can see temperature versus time. And the solution here are all the...
We can't.
Oh, that helps if I hit.
I thought we were supposed to sort. I saw right. I'm like,
Thank you. But this particular freezing point plot, it's not, remember, the thing we're studying, the thing that's going to make this kind of plot is in the ice bath. Okay, the ice bath is just a cold sink, if you will. And what happens is that these different solutions that we make up from parts A and B, there's a part C, but I'm just going to give you data from that one. You're going to try to get a freezing curve that looks something like this. And this is, and I'm going to demo one of these because, I want to show you a couple little tricks to getting this thing to work. But typically, when you do one of these freezing point curves, it doesn't actually, if it can, there's a certain temperature at which the solution is going to freeze, okay? But as it turns out, when you're actually monitoring the temperature, there's going to be usually a little point there where it actually goes into like a super saturated, super cooled kind of scenario, and the solute particles, they haven't quite lined up with each other. Okay, it takes a little bit of time, and probably some agitation helps as well, and then it can trigger the solid particles to actually align themselves properly and then come out as a solid. And when it does that, then you get this sort of classic plateau, which is actually, that'll be the new freezing point that we'll record for our data point for each of those parts. Okay. Now, the temperature at which a solution freezes is governed by, and let me just add a new page. Okay, it's adding it to the end, that's fine. But this freezing point depression, it follows this particular equation. So it says that, it's in the book, it's in the notes, in the lab, it's all over the place. I'll just rewrite it here. It's that the change in temperature from the original freezing point of the pure substance is going to be equal to this equation, negative I, which is I'll go into, KB, which I'll go into, and little m, which we've already seen, molality. Okay, so it's only 3 variables that we have to worry about here. The one that we've already talked about and we've already seen, the little m, I'll just sort of put it off on the side. Molality, remember that is moles of solute and then kilograms of, and it's kilograms of solvent, yes, but since we are controlling what solvent is in this lab, I'm just going to go ahead and ink in as kilograms of water, which is what you'll use for this experiment. Again, the water is our solvent. Let's talk about the other two, from easiest to more challenging, and it's not that challenging, but let's talk about KB. That is the freezing point depression constant. Very creative name. Freezing point depression constant. And this, what you need to know, is a function, or I should say, it depends on the solvent. Let me put it that way instead of function of. This depends on the solvent. Since our solvent is water, then I can just give you the literature value. If you want to write out, one form of it, K sub B, and you can You can put all kinds of little subscript tags telling you what you're talking about. But the freezing point depression constant for water comes in at 1.86 degrees Celsius per molality unit. That constant is just simply telling you how many degrees Celsius this thing is going to drop by the freezing point per molality of concentration. So if you had a solution at 1 molal solution, then you might expect that this aqueous solution would freeze at minus 1.86. Okay? So remember, that is the amount that it's going to decrease from the original pure solvent. And we'll apply that and sort of see how that works a little bit. Yeah, we'll kind of do it here. We'll definitely do it in class. All right. And then the last thing here, the I, that is referred to something called the Van't Hoff factor. Oh, there's an N in there. Van't, and there's a little apostrophe there. Van't Hoff factor. Some dude named Ben Hoff, I'm sure, this is named after. But that I, it represents a number of particles that form in solution. Let me give you just a couple of examples of that, give you an idea. Examples: sodium chloride. When sodium chloride goes into solution, how many particles? 2. We would say I is equal to 2. So it's basically the number of ions that get kicked off as something dissolves in solution. If you have something, let's do ferric sulfate. Yeah, Fe2SO4 3. This is where little bit of ionic structure and be able to pick apart these ions quickly can save you some headaches. And I know it's been a while, so that's one reason why I'm choosing to go through all those. And if I really wanted to care, and I guess I sort of do, I shouldn't have done that, because I should really say that's a solid. But I should probably add an AQ tag all the way through. Later in the semester, I will not do that. Basically, you assume that if you see an ion just floating around by itself, assume that it's aqueous. Okay. But yeah, you got 2 cations, you got 3 anions, so I is equal to 5. So you can see that go away. So you can see that as that increases, then you can get a fairly dramatic decrease in that freezing point of the sample. One practical example that you see in DOT, when they salt the road they're basically using this freezing point depression phenomenon to keep roads from freezing up when inclement weather is coming through, sleet, whatever. And you could use sodium chloride for that, and you get an I equal to 2. But a lot of times what they'll do, especially, this is my understanding, if they know a storm's coming through and they pre-treat, especially the interstates, they'll put a solution of calcium chloride on it. And calcium chloride has an I equal to 3. So it has a little bit more oomph when it comes to keeping the roads wet instead of icy in those storms. Now, obviously, all bets are off if you're down to, 20 degrees Celsius, something like that. Forget about it. There's some cutoff where it's not going to matter. But, it's going to work very well for, especially our area. I mean, it's not like...
Doesn't even salt that much usually.
Yeah, I mean, like -1 degrees Fahrenheit. I remember that's the coldest I've seen it at my house in the, 14 years or so I lived there. That was once, maybe twice. It's not like really cold. But anyway, so just a little bit of info there for you.
Can you go back to that? Yeah, just
Yep, I'll pause for a second.
So with this formula, how are we actually going to solve for like the freezing point? I guess we're kind of given the freezing point.
It depends on what we're doing. So like, I'll give you sort of a quick rundown. In part A, we are going to be calculating KB. And then in part B, we're going to calculate Van Hoff factor. And then in part C, it's not even that. There's a variation on this where we can calculate the molar mass of a substance. Okay? So it just depends on, or we could just be calculating the delta T for a solution, right? Any of these could be possible. I will comment that, like, if you're calculating delta T, that delta T value then needs to be subtracted from the original freezing point of the solvent before you get the new freezing point, okay? Water typically freezes at 0 degrees Celsius. If we do an experiment and we say, well, the delta T should be equal to 4.8 degrees Celsius, then, to get the actual freezing point of the new solution, it would be 0, the original one, minus that 4.8 degrees Celsius, which obviously for this would be minus 4.8 degrees Celsius.
So whatever we observe the freezing point to be, we just take the 0, which water would usually freeze at, and then we're subtracting from it.
Well, if it's water.
If it is.
Yeah. And then in the example in class, I use a solvent called chloroform, and it has a different freezing point, has a different constant, and then you got to do the same thing. And it's like, if you calculate the delta T, then you got to subtract it from the original freezing point of the pure solvent. And we'll see that. Yeah. But just like any type of equation, there's all these little things you sort of have to keep track of as you're plugging and chugging along. The last thing I want to comment while I'm looking at this equation is that pesky little negative sign in front of this expression. Sometimes that is not there depending on what textbook you're looking at. I choose to add it there because it reminds me that for the freezing point, it is being depressed, it's being decreased. In other examples, and actually Brown and LeMay may do this, Brown and LeMay may just leave out that negative sign, and you just have to know that the freezing point is going to decrease when you're using this equation. Okay, so just be aware that, just like I've said quite a few times, it feels like about negative signs in our class, oftentimes it's just giving us a direction that the change is going, and that's certainly the case for this example. Before I leave this, I almost forgot something. There is another example we need to know for the Van Hoff factor, and that is for a molecular compound. The very first lecture that I did, first lab review of like 151 material, I talked about like how can we identify molecular versus ionic substance. I was thinking of this moment. Right, all of these up here, these are ionic because we see the metal in front in the formula. For molecular compounds, and C2H6O2, that would be a molecular compound. Do I need to know all the details about how the carbons and hydrogens, the oxygens? Nope, I don't. I don't need to know how they're connected. If it's all non-metals sitting there, then I know that it's a molecular compound. When this one goes into water, it's actually ethylene glycol. It's what we're using in part A. If when it goes into water, all it does is it dissolves. So, you know, from chapter 4 language in 151, we'd call it a non-electrolyte. Okay, it goes into solution, and we would say that I is equal to 1 in that example. So all the molecular compounds you might come across, I is going to be equal to 1. I'll go ahead and give you the other one that you're going to see for this lab. In part C, we use something called urea. It has the formula CON2H4. And then same kind of thing, when it goes in solution, it's a molecular compound, so it doesn't dissociate. And so that I is going to be equal to 1 there as well. So for the molecular compounds, you know, if I is just 1 sitting there, you may even see examples where it's omitted. I wouldn't be surprised. Okay, but the negative I KBM I think is really represents more of the full equation for our freezing point depression. I'll demo the lab in a second so you sort of see how. Let me go. Oh yeah, add it to the back page of this. But yeah, the procedure part. I'll basically talk about that when I do the demo. Let's pick apart a few little things here while we're looking at it though, and I'll break it down from part A, B, and C. I'll keep it kind of together. In part A, you're trying to calculate the KF of water. Now again, the literature value is 1.86. I gave you a few minutes ago, but we're gonna try to see if we can reproduce that in lab, and we do that using ethylene glycol, which is that compound I mentioned just a few minutes ago. It's molecular compound I equals 1, and there's 3 trials here. There's one that's running at 0.5 grams. One that will be run at 1 gram of ethylene glycol, and then this 1.5, that one I'm going to demo. And that way I can show you kind of the mechanics involved in how we're going to actually make up the solutions and stuff like that, sort of hopefully as efficient as we can. And I'll probably do that calculation, even though I forgot to bring in the calculator.
Is this 3 times for each one?
No, just 1 time each. Yeah, there's a total of 3 trials, and I'm doing that last one as a demo. I think in the when it says 6 medium-sized test tubes, that's for like the entire lab. So 3 used here, 3 in the next, 2 in the next. Doesn't matter. We're not going to do the entire thing. Okay, so you don't actually have to get 6 medium test tubes. But notice, there's the equation I gave you. We solve for KF right there. And so that's the formula you'll use to calculate KF for water there. And I'll do an example of that in a minute. Part B, we're going to try to figure out the Van Hoff factor. So just look at the equation real quick. I've just taken that original equation. I solved for I. Notice the negative sign is missing. That's not unusual, again. So just know that I will be positive. If you follow your typical rule about delta T's and blah, 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 you may even come out with a negative value here, but again, the negative just reflects that the freezing point decreases. Right? There can't be a -1 particle in solution or -2 particle in solution. There's 3 listed here. It gives you recommendations about the mass of the solutes you use. 1.75 grams of the calcium chloride, 0.58 grams, not 0.75 grams of the potassium chloride, 0.85 grams of sodium chloride, and then the calcium chloride we are going to skip there. We're not going to do that one. And each group will do one of these. Pick one, doesn't matter. Okay? So you'll do one experiment from part B. You'll do both here. So 2 from part A, 1 from part B, and that's all you're doing for this lab. Well, at least experimentally. There's some additional calculations and stuff like
So
that.
just like pick 2 and 3, like half a gram, or 1.5 grams.
Now, so part A, you'll do both of those.
Yeah, part B, we're only going to be filling out one of these.
One, yes, I got you. Yes, just one of those
We're not
columns.
doing calcium chloride.
Yeah. And then finally for part C, I am going to give you that data. But here's the equation. This MM is the molar mass. And, working through sort of, the original formula and getting to the molar mass equation here, it's not a lot of heavy lifting. I did it sometime in the past, but I'm not going to go through some kind of derivation here. It's just sort of there. And by the way, this will be on the test. The equation is in the lecture slides for chapter 13 as well. Okay, and I'll reference it tomorrow when we do that.
Our test is next Wednesday?
Next Wednesday. Yeah. Yeah, I should be able to finish 13 tomorrow. I'm pretty sure. And I did post. I forgot to post the videos this morning. I posted them before class, so those videos are out there.
So Monday will be like a review class?
At least some of it will be. I'll probably need to use some of that time for chapter 14 just to get through some of the basic stuff of chapter 14. I'm not going to do some like the crazy stuff for 14, but just sort of basic concepts of 14. Kinetics, I will spend some time either tomorrow or Monday doing that. Yeah, but yeah, I am planning on doing some review on Monday. Yeah. Okay. We'll look at the report sheet in a second. Let's just take a quick peek at the post-lab questions.
There are no pre-lab questions?
Yeah,
Okay.
no pre-lab. Yay. So on the post-lab questions, both of these are dealing with that Van Hoff factor. The first one is just asking you to figure out the Van Hoff for each of those. And then in the second one, where is it? Yeah, you have these different solutions to think about. Well, there's 6 different solutions that it's giving you. And it says, imagine each one is the same concentration, and which one is going to freeze? Which one's going to have the lowest freezing point? That is a Van Hoff factor there. Because if you have the same solvent, so Kf is the same, it says you have the same concentration, think 1 mole, and then that only leaves Van Hoff as the deciding factor about which one's going to have the lowest freezing point. And remember, the one that produces the greatest number of particles is going to have the lowest freezing point.
So would it be safe to say like as I increases, so does delta T?
Yeah, we can write that in. As I increases, delta T increases.
Whoever has the biggest Van Hoff.
Yep. Problem number 3, okay, it's asking you to figure out the new freezing point, basically. It would be the minimum temperature, etc. Yeah. Or right before freezing, I guess, is the way I should say that. And the context here, okay, you're going to need to calculate the delta T based on the information there. And let's just look at the delta T formula. Sodium chloride, I've already mentioned, right? That's NaCl, I equal to 2, so I've already talked about that. Kf, I've already given you that because we're assuming all solutions are aqueous unless otherwise mentioned. And this one actually tells us it's in water, but that was 1.86, that's degrees Celsius per molal. So that really means the heavy lift here is calculating molal. Real quick, let's just think about that for a minute. We need moles of, I'm going to write it specifically for this problem. I would need to know the moles of sodium chloride and divide that by the kilograms of H2O. And that information is embedded within there. You got to do a little bit of calculations here. What does that 35 grams per 100 milliliters mean? That means 35 grams of sodium chloride. This is like a solubility type of formula, and so that 100 milliliters here is referencing water. So those are what those two numbers. That's what those two numbers mean. So basically, you need to convert grams here to moles of sodium chloride. You'd use the molar mass to do that. And then to go from milliliters and depending on to kilograms of H2O, you're going to need the density. It's not given in the problem, but I will say this, okay? At this point, we assume, the royal we of academia, chemistry academia, that you know that the density of water is 1 gram per milliliter. So, 100 grams equals 100, oops, I did that backward. 100 milliliters, which is given to us, is equal to 100 grams, and then you can convert that to, I'm giving the answer, 0.1 kilogram, right? You're just dividing by 1,000. That essentially moves the decimal over 3 places. So the heavy lift there is getting molality out of the way. And I've given you, I think, a reasonable amount of structure for that one. And then finally, this last one is kind of busy, but that's fine. We want to take a look at the molar mass formula. So molar mass, molecular weight, they are different. Molecular weight is an AMU. That's the mass of a single molecule. Molar mass is the mass of a gram or a mole of those molecules. But it's the same numerical value. Right? So I'm going to use molar mass. I'm just going to read out that formula real quick. We got the Van Hoff factor, I, up top. We got Kf. And then grams of solute. And that's its own thing. I'm going to put parentheses around here just to sort of separate all of them clearly. And on the bottom, you got the delta T sub F and kilograms of solvent. What data do we have? Well, we're told the mass of the solute, check, grams of solute. We are told that it is a molecular substance. So that means I is equal to 1. Right. Kf was already given. That's 1.86. The delta T, just telling you, temperature's dropping by negative 1.2. degrees Celsius. And then finally, we're given the amount of solvent in grams, and we need to get kilograms. So kind of a classic, plug and chug, where you got to go through your problem and pick out the little components you need, and just making sure that units agree and you interpret I correctly and stuff like that. And again, there'll be at least one of these calculations on the test next week, some variation on this.
What are the units on
KF is degrees Celsius,
KF? Over.
molality,
There's
molal.
no units on I, right?
Correct. Yeah. Yeah, we'll add that. I is unitless. Okay, there we go. Report sheet. Let's make some notes. What we're doing. First, what we're not doing. We're not doing calcium chloride. Of the two that are remaining, again, just pick one. Doesn't matter. Part A, you'll do the first two. Do these. And then I'm going to demo and record the data. And I'll probably crunch through the numbers too real quick for you on that one too, just so you can sort of see how all the pieces fall together. Now, before I move on to C, let me just make a little comment here. When you read the lab manual, one thing it asks you to do is use your average KF value from part A to do these other calculations. We're not going to do that. Okay, so if you don't mind, go ahead and ink in, well, first off, just mark out from part A. And we're just going to use 1.86 for all of those parts down there.
So does that mean our average KF should be around 56? Like it should be close to that?
It'll probably be larger. Yeah, there's some challenges in part A trying to get that KF correct. I think I mentioned in class yesterday I was messing around with these kind of things called molecular sieves, trying to dry something. I'm trying to dry the ethylene glycol. It hit me yesterday. I was like, I bet there's water in that because it's very hygroscopic, is my guess. It's an alcohol. It's going to pull in the water from just sitting out. And so I put in some molecular sieves. It's over there. I'm looking at it, and I'm hoping that dried out the water a little bit. It'd only been soaking in there for overnight, so we'll see if it see if it does anything. That's one reason why I want to demo that 1.5 example. Yeah, let's actually let me do this demo so we can move on with our day. Now, I'm going to take a few shortcuts. Forgive me. I don't think you'll mind. Like, for example, initial freezing point of water, we're just going to say that the world is behaving perfectly for us and say it's just 1, okay? Or 0, sorry, with 0. Mass of the water, and I'm looking here. Actually, the things you have control over, what you will measure, put in a different color. You'll measure mass of water. You'll measure the mass of ethylene glycol. And then the only other thing you'll actually measure is the freezing point of water. These are measured. Okay, and all the other ones you'll calculate. All right. So let me sort of go through this and see how bad everything can get. The setup here is going to, and I'll just leave that recording and we'll see how well it picks up my voice. obviously it won't. If you watch the video later, you will not be seeing any of me. Anyway, we're going to use our large ignition tubes. I think it's good general practice to label whatever you're making, just so you know what's there. And instead of, these are so large, we're going to use 250 milliliter Erlenmeyer flask just to hold this thing together as we do the experiment. And I said we are going to measure the mass of water and the mass of the ethylene glycol. We're going to do that on the balance. Now, if you look at the procedure, it asks you to measure out 10 milliliters of water. And so I'm just going to use my squirt bottle. I'm using distilled water mainly because it's convenient in the squirt bottle here. I'm going to take it up approximately to 10. That's close to 10. It's maybe a little bit over. It's fine. And then on the balances over here, if you can't see the balance, you'll kind of want to scoot around so you can see what I'm doing. I think this will save you a lot of headaches. And these balances, you know, there's doors all around, including the top. We'll actually use the top door today. And these balances can handle this heavy setup, which is really nice. It's weighing in at 178 grams. That's fine. I'm going to zero it out. Zero. I'm going to take my test tube out, or ignition tube, and then I'm going to add my 10 milliliters of water. I'm going to put that back in there. I'm going to measure that. It beeps. Like, when is it okay to record the numbers? This one beeps. And also on the left-hand side of the display, there's a little circle that pops up while the balance is still thinking. And then when it beeps, the circle goes away, and that tells you you can measure it. 9.9086, 98.6. $9.98.6. I think it's what it is.
086.
0.86. I just didn't say it. Unusual. That is close enough to 10 for us, okay? And then I need to add approximately, again, this one's 1.5 grams of the ethylene glycol, or this one is 1 gram, this one's 0.5. So I'm gonna do drop by drop of the ethylene glycol from the top door and wait until I get to about 1.5. And to do that, I can just hit tear again to zero it out. And if you make a mess, it's okay. Let me know if some of this gets on the balance, and I'll get some acetone or something to clean off, because this is kind of a heavy liquid. But just be a little cautious. And I'm just going to rest my hand on the top of the balance. And I don't know how many drops, but it's not many. I'm already at 0.4, 0.5.
You
0.7,
need a pencil, please. What's that?
1.2, 1.3. I went a little over, but that is okay. I'm at 1.5302 grams. Write that down. What did I say? 1.5203 grams.
53.
53. Thanks.
Should we write that after you?
Yeah.
Yeah, because I was thinking maybe we have to do that.
Yes. Oh, 2. Yeah, you should write down these numbers, because you can use. I'll do the calculation, and then you can use that as one of your variables when you do the average. So. And it shows you some structure in terms of. Oops. Yeah. And now I got a solution in here. I didn't make a mess. Yay! Again, if you make a mess, it's not the end of the world. I'm just gonna mix it up a little bit. Now I had my temperature probe in salt water. You won't do that. I need to clean that off before I stick it into the solution. And actually what I'm gonna do, let's go with water too. It's salty. I'll talk about the ice bath. Very simple to make up. I'll tell you all about it in just a second. And I'm going to stick the temperature probe in the solution, and I'm going to go back to I think it's that. Yay. Stop. Remember, if you want to clear this thing ran the whole time while I was yakking. It's the wrench and the screwdriver is the one that you want to use if you want to clear the data runs. And I'm going to hit start. And right now it's room temperature. And scale it. There, that's better. And this ice water bath, right? This thing was at something like minus 12 or so. Well, it's easy to make a mess, so I'm trying to keep it away from my devices here in case it splashes out. And just keep it constant stir the whole time. Like I showed earlier, for some reason, if everything's moving, it's colder. I can't explain why. I should have jumped back to that idealized freezing point curve that was on the first page of the lab. I'm still not even below 0. There, close.
Can it be that because you make a reaction to happen?
I mean, it's
Like
you
it
gotta.
was in stable position, but since you decided to interrupt the freeze, it started again, and that's why it came over.
There's got to be something I'm disrupting. Yeah, could be some interaction between the salt molecules and water, possibly. I don't know, but something's getting disrupted. Honestly, it just hit me. I may not have enough ice in here because I set this thing up about an hour ago. Remember what happens here, it's supposed to super cool and then pop back up and then plateau off. That's what I'm looking for. Look at that. There's my plateau, I think. Okay, so that's fairly typical. And then the last thing I want to do, yeah, it's frozen. Okay, good, wow. It behaved exactly like I needed it to behave. Yay!
And then we record it on the plateau.
Yep.
So the delta T is negative.
Yep. So the only thing we need, remember, I like that button there for measuring the temperature or whatever. And it's coming in, 5.1, 5.2. We'll do 5.1. Why not?
And that's the final freezing point.
That's the final freezing point, yeah. Yeah, so let's do this calculation real quick. And I don't have a good calculator, but I do have this thing. Okay, so I'm going to zoom in so I can get some room to write. Okay, so if I want to calculate the number of moles, that's the number of moles of the ethylene glycol. That's going to be, and notice we give you the molar mass there. So it's going to be this number divided by the molar mass, 62.1 grams per mole. And that is something. 1.5302 divided by, oops, and I just goofed up. 1.5302 divided by 62.1. I am getting, yeah, and let's, I guess we're doing, I'm going to do 5 sig figs on this one, and I'll tell you why in a second. So 0 to 5 more digits. 24, 64, 1. 1. So that's my number of moles. And then going from grams to kilograms, just dividing by 1,000 there. So that's going to be, actually you can say 9.9086 times 10 to the minus 3. Is that right? 1, 2, 3. Yeah. That works. And then if I want molality, which I do, it's actually these two divided by each other. And I'll just write it out on the side. So 2464.1 moles divided by that 9.9086 times 10 to the minus 3. Let's see what that gives us now. Actually, yeah. 0.86. And hopefully 2.48 something. Cool. So it's, and I'm going to do, again, I'll talk about sig figs in a minute. We got 5 and 5, so we'll do 5 sig figs again. 2.4868. And then notice that, like for this one, we measured the freezing point, change in freezing point. It's the same value, but I'm going to just turn it positive just so the KB value is, or KF value is positive. It's kind of like, to get this number, I said 0 minus that number, 5.8.
So now we just act like we know the KF value is probably 1.86 and just plug everything else in.
No, because this one, we're actually going to calculate the KF, and that KF is going to sit, well, the KF formula, let me just go full treatment here. The change in the temperature of the freezing divided by I divided by M. And since I is just 1, it's essentially delta T divided by M. Remember, ethylene glycol, molecular substance, I is equal to 1. And so that molality divided by, delta T divided by that molality. That's 5.1 divided by 2.4868. That's better than last year, I think. Yeah. And that's degrees Celsius per mole. And sig figs here would dictate 2.1 sig figs. Let me talk about sig figs just real quick here, because I know I flew through it real quick. For sig figs, I'm going to put a number with a circle around it for each one. Sig figs, when you're doing a sig fig calculation, sorry, let me back up for a minute. Remember, one thing I said about sig figs, on the test, don't worry so much about sig figs. That's just not going to show up. But labs, that's where the sig figs show up. Maybe mastering chemistry as well. Right? So when you factor in sig figs in an experiment like this, I use the sig figs from the actual data that you collect, okay? Because that's where the error is coming from. The mass is over there, and the temperature, those things in green that I just highlighted over here with the asterisks. Those are the things were measured. So when I look at sig figs here, you know, these first two numbers sitting here, right? They're all non-zero, or the zero is in between non-zero numbers. So all of those digits are significant to the measurement. And it's because we have such a good balance. There's 5 sig figs in that one. There's 5 sig figs in that one. So that means that any kind of multiplication or division problem that I do from here on out, which is what I'm doing, to get, right? Here I said I'm going to use 5 sig figs. Here I use 5 sig figs. There I use 5 sig figs. Again, because it's our original data. But then, when I got down to this problem, my sig figs shrunk. And I just have 2 sig figs in that temperature value. That dictated, in a roundabout way, the 2 sig figs there. And then since this was division, right, I can only keep my first 2 significant figures in that final answer. So that's why I rounded it up to the 2.1 there. 2.1, that's a little better than what I've seen in the past. I'll be curious next week if that is drier and it's even a better data point.
So can't you calculate like how off it is usually? Isn't it like the expected value divided by something?
Yeah, it's like yeah, experimental minus theoretical or literature. That then you take the absolute value of that if needed, and then divided by theoretical. Yeah, times 100. Yeah. We don't want to know our error. No, sometimes we do, sometimes we don't. We don't worry about it right now. And is it going to work for me? Yeah, sure it is. Okay, I'm almost done. I just got to do one more with the part C. But again, right? For y'all, where's my pen? Oh, I think it's that. Okay. Right. You're going to do both of those. You'll do one of those. Pick either one. And then for part C, I'm just going to give you the data. Where is it? There it is. And just like I said a minute ago, we're going to assume the freezing point of water is 0. In this particular one, I measured out a mass of 10.3867 grams of water. 10.3867. And then a mass of urea of 0.605. And then the final freezing point was minus 1.7 degrees Celsius. And then from there, I'll let y'all do the rest of the calculation. And just notice in this bottom part, the last 2 lines, you're asked just to compare experimental from theoretical. Theoretical is just what you normally get when you measure off from the periodic table, the molar mass there.
What's the
urea, it is, it's this urea. I'll give you the structural formula here. NH2, CO, NH2.
What year we got?
And I guess the last thing that I can think of is the actually setting up the ice bath. What I did, I would use 2 coffee cups, and everything will be mostly on the side counter over there or up here. Actually, I'll take the salt back there.
Do you wear gloves or eye protection?
Yeah, let me think through this real quick. But when you set this thing up, I have a big teaspoon in here, a heaping scoop of this in the cup. Put in a little bit of water, maybe about 100 milliliters, sort of dissolve that a little bit, and then 1 scoop of ice. 1 scoop of salt, 100 milliliters approximately, and 1 scoop of ice. And I'll bring the ice in. And then, yeah, that solution cools off pretty quickly. You don't have to wait too long. And I'll put the ice back here as well. Ignition tubes back here, label tape with pins. Of course, the coffee cups there. Oh yeah, I did not go through the setup for these things. Well, one thing I'm going to do is turn this off because I don't need to do this anymore.